Welcome once again to have a discussion on fundamentals of sensors and transducers. In the previous session, we had discussed about requirements of sensor interfacing, units, detectable phenomenon, physical principle, need and selection of sensors, and how to select the transducers. In today's session, we are going to discuss about performance and terminologies. So performance basically depends upon the range, span, errors, accuracies, non-linearities, deadband and saturation, and moreover some of the performance characteristics are also there. So in today's session we are going to discuss some of the characteristics like range, span, error, accuracy, non-linearity and deadband saturations. First of all, we will talk about the inputs and outputs. In case of sensors, input is nothing but stimulus or measurand that may be a temperature, pressure, light intensity, etc. An output can be an electrical signal. It may be voltage or current or frequency or phase. So there are certain variations. So output can sometimes be displacement like thermometers, magnetostrictive and piezoelectric type of sensors. So some sensors combine sensing and actuations as well. When we talk about the actuators, so input is basically electrical signal that can be a voltage, current, frequency, phase, etc. And output can be a mechanical, like it can be converted, the electrical signal is converted into force, pressure, displacement, or display function like dial indication, light, display. Okay. Now we'll talk about the transfer function. So basically transfer function gives the relationship between the inputs and output. And another name for this is input output characteristics function. It is also known as a transfer characteristic function and response. So transfer function can be linear or non-linear. It can be single valued or not, or one dimensional or multi-dimensional like single input or single output, multiple inputs and single output. In most of the cases, it is difficult to describe mathematically, so it is given graphically, and often it is defined from calibration data as well. Also, it can be defined on a portion of range of the device as well. Here if you can see, so T1 to T2 is specifically a range of temperature and it is approximately linear as you can see in the form, as you can see in the graph. So it is a most useful range that is between T1 to T2, and typically a small portion of the range it is, and it also often taken as a linear as you can see. What are the other data from the transfer function we can describe, like saturation, sensitivity, full scale range, hysteresis, deadband, etc. There are other types of transfer functions which gives a response with respect to a given quantity, and performance characteristics like reliability, cost, etc. It can be viewed as a relation between any two characteristics. Now let's take a look at range and span. So range is nothing but the lowest and highest values of the stimulus or quantity, and span nothing but the arithmetic difference between the highest and lowest values of the stimulus that can be sensed within the acceptable errors. What is the input full scale? So generally input full scale always equal to a span, and output full scale, it is the difference between the upper and lower ranges of the output of the sensor corresponding to the span of the sensor. Now we will talk about the dynamic range. So dynamic range is basically a ratio between the upper and lower limits and is usually expressed in dB. Let's just take an example. A sensor is designed for minus 30 degrees Celsius to plus 80 degrees Celsius to give an output of 2.5 volt to 1.2 volt. So range is from minus 30 to plus 80 degrees Celsius, Span will be 80 minus minus 30, that is 110 degrees Celsius. Input full scale will be 110 degrees Celsius, because as we have seen that input full scale is equal to span, and output full scale is the difference between the highest value and lowest value of the output, that is 2.5 minus 1.2, that is 1.3 volt. And dynamic range is nothing but 20 log of 140 by 30, that is 13.38 dB. So range, span, full scale and dynamic range may be applied to actuators in the same way. Span and full scale may also be given in dB when the scale is large. In case of actuators, there are other properties that come into play, that is maximum force, torque, displacement, acceleration, time response, delays. Now we'll talk about accuracy, errors and repeatability. So what do you mean by an error basically? Errors are nothing but the deviation from the ideal value. And what are the sources of errors? What kind of material you are going to use, then construction tolerances during the manufacturing, then aging, operational errors, calibration errors, impedance matching errors or loading errors, then certain types of noise, many other sources are there. Errors are basically defined in different ways. First we see as the difference E is equal to V minus V0. So V0 is the actual value and V is that a measure value. So stimulus in the case of sensor or output in case of actuators. As the percentage of full scale, that is span, for example, E is equal to del T by T max minus T min into 100, where T max and T min are the maximum and minimum values the device is designed to operate in. So in terms of the output signal expected. Just take an example for error. A thermistor is used to measure the temperature between minus 30 and plus 80 degrees Celsius and produce an output voltage between 2.8 volt and 1.5 volt. Because of errors, the accuracy in sensing is plus minus 0.5 degrees Celsius. In terms of the input, as plus minus 0.5 degrees Celsius, the percentage of input E is equal to 0.5 divided by 80 plus 30 into 100, that is equal to 0.454%. So in terms of output from the transfer function, E will be equal to plus minus 0.059 volt. Here you can see for that particular span how from the transfer function we can calculate E, which is equal to plus minus 0.059 volt. Now there are different types of errors are there, like static errors which are not time dependent. Some are the dynamic errors, like time dependent errors are there. Random error means different errors in a parameter or at a different operating times. There are certain systematic errors also. So errors are constant at all times and conditions. Now we'll talk about the error limits, that is linear transfer function. Error equal along the transfer function. Error increases or decreases along the transfer function, and error limits nothing but the two lines that delimit the output. For nonlinear transfer function, error changed along the transfer function as you can see in the diagram, and maximum error from the ideal value and average error. The limiting curves follow ideal transfer functions. Calibration curve may also be used whenever it is available. So it indicates the lower errors, maximum error from the calibration curve, average error. The limiting curves follow the actual transfer function. Now we'll talk about the nonlinearity. A property of the sensor introduced by the errors. So nonlinearity errors influence, definitely it influences the accuracy. So nonlinearity is defined as the maximum deviation from the ideal linear transfer function. and latter is not usually known or useful. So nonlinearity must be deduced from the actual transfer function or from the calibration curve. There are few methods to do these things. First is by use of range of the sensor or actuator. Just you have to pass a straight line between the range points and calculate the maximum deviation of the actual curve from this straight line. And good when linearities are small and the span is small for thermocouples and thermistors especially. It gives an overall figure for nonlinearity. Second method is by use of 2 points defining a portion of the span of the sensors or actuators. Again we have to pass a straight line between the 2 points, extend the straight line to cover the whole span, and calculate the maximum deviation of the actual curve from this straight line. And it is good when a device is used in a small part of its span. For thermocouple, which is used to measure the human body temperatures, and it improves the linearity figure in the range of interest. Another method is use a linear best fit, that means least squares, through the points of curve. Take endpoints on the actual curve, xi, yi is equal to, so I can be in 1 to that is up to n. Assume the best fit is a line, that is y is equal to ax plus b, and calculate the a and b from the following two equations. And one more another method is there. Use a tangent to the curve at some point on the curve. Take a point in the middle of the range of interest, draw the tangent and extend to the range of the curve, and calculate the nonlinearity as previously. Only useful if nonlinearity is small and span is very small. There are certain other parameters also there, like a deadband. The lack of response or insensitivity of a device over a specific range of the input. In this range, which may be small, the output remains constant. So device should not operate in this range unless this insensitivity is acceptable. For example, an actuator which is not responding to input around 0 may be acceptable, but one which freezes over a normal range may not be. Okay. Now we'll talk about the saturation. So basically saturation is a property of a sensor or actuators when they no longer respond to the input. So usually at or near the end of their span, and it indicates that the output is no longer a function of the input, or more likely is a very nonlinear function of the input, and it should be avoided because sensitivity is small or non-existent. In case of actuator, it can lead to a failure of the actuators, like increasing power loss, etc. So that's all about today's session. Let's recap some of the points what we have covered today. So we have discussed the performance and some terminologies like range, span, accuracy, errors, linearity, non-linearity, deadband, saturations, okay, and various sources of errors as well. So thanks for your kind attention, and we will have some more sessions on fundamentals. Stay tuned. Thank you so much.